everyone. Today we're going to talk about a full spectrum of IoT and dive into the challenges that we see in technology and in intellectual property in meeting the vast markets of the Internet of Things. I have a few slides up front, just sort of introducing the topic. I won't be staying long on these particular slides, but you know, when you're trying to make sense of this Internet of Things landscape, you know, it's important to sort of understand that it's a collection of smart devices, and basically these devices are communicating and collecting and analyzing data as well. So while you have a collection of these devices, you also have the need to be able to analyze big data. And so the needs for technology and intellectual property cover quite a broad range. The Internet of Things can be considered as an extension of a person or a machine, and it's a productivity tool. And really, the Internet of Things is the next revolution in computing as well. So IoT, as you can see, these are just sort of a collection of graphics, that's sort of the buzz that's out there. But depending on who you talk to, it's a very, very, very significant market. And it's a significant, very high growth opportunity for semiconductors. So if we dive a little bit deeper, looking at the segments for semiconductor, you can see that the semiconductor markets, if we really kind of look at them at a high level, you see connected homes, connected vehicles, wearable systems, connected cities, industrial internet, and then down below these items, you know, you get into looking at utilities, using smart devices for telematics and automobiles, reduction of town time and energy conservation, efficiency on capital goods, healthcare, optimization of the human capital in hospitals, for example, connected cars, smarter logistics for transportation, and then of course we're all pretty aware of consumer wearables that many of us have today. And then this also affects our home, being able to track different security, any of the things that we have going on in our homes as well. So what I'd like to do is kind of dive into these and sort of partition these segments, these semiconductor segments, and really start looking at where they fit as far as process nodes, technologies, and intellectual property. So when we start looking at process nodes, we can sort of separate this into things, mobile, and networking and computing as the three main segments as far as looking at how we can partition technologies and as well as intellectual property. So on the things aspect on the left there, ultra-low power with best density for low-end sensors, low-end MCU-powered IoT devices. These devices in that first column will utilize process technologies from 180 nanometer, and some may go into the 40 nanometer technology range, but they're likely going to use the older, more mature technologies, ultra-low leakage, low leakage, ultra-low power, low power technologies. The next column and the next segment, if you will, sort of following up the performance trend, is low power and high performance for mid-end MCU-powered IoT devices. These will use 40, 65, 55 nanometer technologies. And moving forward, the sweet spot really will be 40 nanometer for these particular devices, and they'll be using ultra-low power and low power technologies. And then third, under the things, are the highest performance for high-end embedded application processor-powered IoT devices, or SoCs. And it will primarily utilize 28 nanometer technologies. These would be high-K metal gate, low power, FDSOI. So there's a range of technology variants as well in the 28 nanometer range. And then for mobile, it will require high performance and high performance compute processing. Of course, one thing to note is across the board, power is a key attribute. So no matter what IP or technology you're looking at for Internet of Things, even in the networking space, you're looking at reducing power as well. And then if you take a look at the networking space, at this point, what you're really looking at is driving the advanced technologies. These are very high performance devices. They're having to manage and analyze and all of the data that's being generated by the quote-unquote things in the Internet of Things. So what we'll do is we'll talk about each of these particular segments and how we can further optimize and understand the types of IP that would be necessary. So if we look at processing, for example, Gardner reported that the 16 and 32-bit processors, or microcontrollers, excuse me, will be at a 2 billion unit ship in 2020. The 8-bit microcontrollers will start to sort of tail off at that point, but that's a huge amount of shipments. So I think it really behooves us to take a look at what's under the hood with microcontrollers, what technologies are they currently at, where are they going, and then how can we best serve them with intellectual property and design services. Also on this curve, you can see embedded processors, both 32-bit and 64, and then the bottom yellow line are the application processors. Up at the right sort of shows the different ways that the microcontrollers are being mapped to different types of markets and devices. So the main thing to concentrate on here is this table. So the table shows you 8 to 16-bit microcontrollers in the first column, and then followed by 16 to 32, and then 32 to 64-bit. And what you can see also in the first row of this table is really the targeted speed. So there are devices in the Internet of Things that are really running quite slow as compared to networking type applications. These could be less than 25 megahertz in operation. So that gives you a lot of opportunity if you're running at a slower speed to really be able to target reducing your leakage and dynamic power that consumes the battery life. These particular devices right now are in the 0.35 micron down to 180 nanometer. And they will stay likely at the 180 nanometer node, maybe some moving to 130. These devices include smart meters, activity trackers, those types of devices. Also some medical devices as well. The 16 to 32-bit range, now you step up to a little bit higher performance, 25 megahertz to 250 megahertz. And then, of course, I forgot to mention that these also include embedded flash, and that's shown, rough content of that is shown in the second row. And with this particular group of the 16 to 32-bit processors, they're currently at 180 nanometer technologies, and these are the ones that are moving down into the 90, 65, 55, 40 nanometer range. The types of devices we're talking about here are smart plugs, smart watches, and the like. The last column is showing 32 to 64-bit microcontrollers. These are now bumping up into performance. They're getting up towards, the half a gig to a gigahertz performance level. And these are now moving into more the 28 nanometer technologies. And the type of things here are home gateways, high-end smartwatches, more high-end devices. So this kind of sets the stage for looking at how eSilicon approaches the Internet of Things. So one thing, I tried to keep this as a minimum, but I just wanted to tell you a little bit about eSilicon. So we're a leading independent provider of semiconductor design and manufacturing solutions, or SDMS. And what we do is we deliver ASICs, custom ICs, and custom IP. And our model is to have fast, flexible, lower risk, and an automated path to volume production. With that, we've developed a series of online tools that you can log into eSilicon.com, and you'll find your way to these particular tools. They include ordering NPWs online. They include our IP marketplace, which is a tool that enables you to browse and download IP. There's a GDS2 and also a WIP tracker. So when you are a customer where we are doing your manufacturing for you, you actually have online tools to be able to track your manufacturing, not only on your computer or your laptop or iPad, but also on your phone. So we've tried to make things very, very flexible for our customers. From an IP perspective, being as though we are an ASIC provider, we have a lot of knowledge and tools in understanding various different designs, SoCs, analyzing process technologies, and really understanding the needs of intellectual property. So with that, we deliver IP both to our own ASICs as well as to our customers' ASICs. And for Internet of Things, we have developed a series of ultra-low voltage, ultra-low power memories that I will be highlighting in this presentation. These hit that sweet spot of low performance, very, very low voltage, low power. We also, on the high end of things, have a series of IP. One to highlight is our ternary CAM that address the explosion of the need to have increased bandwidth at advanced technologies. Some other issues that we're addressing as well is the transition from IPv4 to IPv6 in the networking space. We also, of course, develop fast cache instances as well, where you can kind of trade off trying to have as smallest form factor possible in your particular device while still being able to hit the high speeds that are necessary in the mobile space that we noticed, and in those 32 to 64-bit microcontroller applications. So our portfolio is really broken into three levels: things, communication and networking, and computing and storage. And really these we're kind of lumping together down below. So the types of products that we have are ultra-low power and ultra-low voltage SRAM and ROM. We have some pseudo dual port architectures that I'll cover. Also I'll give you an example of a low leakage SRAM that we have available that I'll put it in perspective of what it was able to achieve in a particular ASIC that we've developed. And these products are available from 65 nanometer down through 28 nanometer. And of course, we also have products on the shelf at 180 nanometer as well. And they cover planar as well as bulk CMOS as well as FDSOI technologies at the 28 nanometer node and below. The products that we have for networking and communications and storage include the ternary CAM. We also do binary CAMs and some custom CAMs for customers as well. So there's a full suite there. Multi-port and asynchronous register files, we actually have these on the shelf and available for you to download, as well as the CAM. We do high-speed SRAM and ROM. We also do high bandwidth memory PHYs. So when we're really getting into this very data crunching, high-end networking space, we have this type of IP as well as interposer design. And then really the technologies here are 28 nanometer down to 10 nanometer. And again, the planar and FDSOI technologies are addressed with these products. if we dive a little deeper and kind of get into the meat of the topic today and look at technology and IP selection, we'll start with IP selection at 28. 28 nanometer really is covering the high end of the quote-unquote things with the 32 to 64-bit microcontrollers, and it's also covering some of the networking space as well. And I don't know if you've noticed, but there's a lot of technology available across multiple foundries. There's multiple technology flavors or variants, if you will, such as high-K metal gate, polysilicon, field-depleted SOI, etc. And it's really become quite a marketplace for trying to figure out that combination of technology as well as intellectual property. There's also a lot of IP providers available in this space. So if we look at this graph below, this just gives you sort of a rendition of what off-the-shelf IP might look like. Now, this IP is across multiple foundries. They're all on 28 nanometer, and they're by various providers and they're on various foundry technologies. And with that, we can kind of see, sort of the space that this IP covers. And what we'll notice is that it doesn't cover this area down here, which is really running into the very low operation, 100 megahertz or below, very, very low power. It's not really hitting that space. Oh, and just to make sure that you can read this, I think I've got my font pretty small, but this is frequency on the x-axis, and this is total power on the y-axis. So this kind of sets the stage here looking at memory IP. And then in the upper right, this is looking at various different standard cells. Now what happens there? Well, geez, you have various different tracks, 9-track, 12-track, 7-track, 8-track, whatever. And so these various different libraries are available to you. With each of these libraries, you have multiple different transistor threshold implants, different channel lengths. So it's not only the architecture of the library that you're dealing with, but it's also these other underlying items that really make a very big difference. In this particular design, we looked at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, almost a dozen different libraries just in this one scenario at 28 nanometer. And this is for a real chip that we were designing. And basically, we were able to find the sweet spot that met the RFQ for this particular design that hit the frequency and the power targets. But this is a lot of work. And so really the idea would be, how do we address being able to hit this particular spot in the curve where we're looking at running below 100 megahertz, really, really super low power. And can we do that at 28 nanometer? And the answer is yes, there actually is an easy button. And with that, I've highlighted an example of a memory that we've developed. This is on a high-K metal gate process at 28 nanometer. And this particular memory is a 1K by 24. And what you see is on the lower axis, the x-axis, this is the operating voltage, and then on the y-axis is the performance. And then I've given you the power at one of the lower voltages that you can see here. What does that do for you? Well, if you can run at a lower voltage, you're saving a significant amount of power. And now we're down at that part of the curve that we're talking about. And yes, this is at the 28 nanometer technology node. So we have a lot of data. I've just kind of given you a very highlight of one particular memory. But another example would be if we wanted to take a look at 28 nanometer in a particular ASIC that we've done. This was on 28 nanometer technology, and it was targeted towards the Internet of Things. And it had 42 megabits of memory in the chip, and almost 17 million gates. And in this, we analyzed in this graph below you'll see in this pie chart. We analyzed basically what were the contributors to the power budget for this particular chip. And what we noticed is that there were really three memories, one in particular, that really affected the power budget. And what we were able to do was to take a proven technology that we have on the shelf and then modify that to further reduce the standby power and the idle power for this particular device. Now, one item to note is, yeah, you can do that, but then what happens when you have an aggressive schedule for first prototypes? Well, you have to start with something that is silicon verified, where you can eliminate most of the risk when you're making changes. And then what we did is we implemented dual voltage rails. We had periphery shutdown. Some of these were already in the design. Some of these were modified slightly. And we traded off higher performance for lower power. So this particular device, we had some room in the performance budget. The memories were running faster than they needed to. So we were able to trade that off. We also implemented a different foundry supplied bit cell in this case. And this bit cell was a low leakage variant. And by dropping that in, that made a significant difference. And we also customized the periphery to reduce the leakage in idle mode. The result, 20x improvement in idle power for this particular chip. We also had 8x improvement in standby power. And we met the schedule. So this is an example of what some customization can do for you while you're going to be using IP that's off the shelf, and there's a lot available at 28 nanometer. There may be places where customizing that IP may bring you a significant benefit. Now this is another example. This is a baseband processor. So this is hitting that sort of that middle section of the original chart that we were talking about. And here what we've done, we have some tools in-house that enable us to quickly take a particular design and map it to different technologies to really look at the different trade-offs in the technologies, both in the variant at that particular node, as well as going from one node to another node. And so in this case, we looked at two different processes at 28 nanometer. Well, actually, this is a subset of a much larger chart, but I'm highlighting two. And basically, these are CMOS and FDSOI technologies were analyzed in the whole analysis that we had done at 28 nanometer. And in this particular case, we can see that we can meet the speed. This gives you the operating voltage differences, so it's sort of 1x to 1.1x the voltage, and you can see the significant reduction that this particular process B brings to this chip. 62% reduction in leakage power, and about that in dynamic power. And then on top of that, there are other things that, if you needed to, then you could go off and do some additional optimization in IP. But if doing this type of analysis, you can hone in with off-the-shelf IP and find the right technology and variant and meet your objectives, well, that's really the key. Now, another aspect is to extend the technology and to differentiate the IP. So with that, I'll give you a few examples. This is a little bit hard to read. I apologize. I think I could make those colors a little bit better for you. But this just gives you our power optimization resume for memories. So we have a host of different optimization power optimization features or management features. These are silicon qualified. They've been implemented across multiple technologies. And what we do is we have the ability to either add or subtract these particular features to really optimize the IP for our particular ASIC or our customer's ASIC. So here's an example. This is looking at wearables targeting medical. This particular case, we're looking at the 40 nanometer technology node. And so again, this kind of gives you that idea of what's available off the shelf across multiple low-power technologies, multiple vendors. And we couldn't find what was really needed for this particular medical device, and so we've developed an ultra-low-power single-port SRAM that meets these needs. And so this chart here basically is giving you the power on the y-axis. It's giving you the performance, which is this orange curve here in megahertz. You can see that the performance range here is sitting in the, above the 50 megahertz range. And then the x-axis is just giving you the total bits of that particular memory. So, these could be various different configurations of memory that sort of fit within this range. And then basically what we have done is we've modified the voltage. So if you take a look, a good comparison would be, this blue box and the green, for example, is looking at dynamic power, but that's at two different voltage levels for operating. And but you can see where we are as far as our dynamic power as well as our leakage, and this really hits a nice sweet spot for medical devices at 40 nanometer. Then looking at 55 and 65 nanometer node, again, reducing the voltage, reducing the operating power, and extending the battery life is really key. So we're targeting in the same type of area, looking at this lower left corner, and this particular device is operating at 0.72 millivolts, and it's operating at 36 megahertz. So you can see basically the dynamic energy consumption. This is for a 24-bit access, and we've given you the conditions that it's operating at. But so this just gives you a couple of different examples, and really there are various different things that you can implement as far as features in the memory. One of which actually is to be able to do some interesting bit cell developments. Foundries encourage and actually demand it at 28 nanometer and below that you use their bit cells because they've pushed their rules, and there are things that they have really tweaked from a reliability perspective and from a manufacturing perspective. But if you're, there are other bit cell architectures that can be looked at and implemented to really run at lower voltage if you do not violate any of the rules, and if you do not require any additional or special implants that typically are used for bit cells that are really, pushing the envelope. So that's yet another area that can be and has been included in some of the memories that we have developed. So now on the other side, what if we're looking at increasing bandwidth for big data? There's a lot of data that needs to be managed out there. So one aspect is this ternary CAN that I was telling you about in the introduction. And, there's a lot of applications. We're finding more and more applications. Networking is a very big business these days. These are two sort of highlighting two high-level areas such as multi-core accelerator engines, Ethernet switches, various different types of switches. And in this, we've found that we've developed several different CAM architectures. Some of these are for our own design. Some of these are for our customers. And, the obvious would be a single port ternary CAM. The way that you read this over here, there's basically single, dual, SD, C is for compare, and basically they'll tell you how many cycles are needed for each of those, as well as read and write. So we have CAMs that we have developed across multiple technologies here at eSilicon, and I'll cover that on the next slide. We also do pseudo two-port architectures as well. So this is an ability to not only offer more bandwidth with a two-port, but also to be able to do this with managing the area and the density as well for our customers. CAMs can be quite area intensive, their bit cell is typically a 16 transistor bit cell. So finding ways to be able to manage both power and density are also key in this particular IP. And then we do, various different other sort of custom solutions for our customers. We have some cams that actually are very, very large, greater than 40, some very much greater than 40 megabits in size. We do do type of architecture where we combine a cam with an SRAM, and so various different architectures that we've included in our particular portfolio. We've built cams for multiple generations across multiple foundries from 180 nanometer down to 14 nanometer. I've given you sort of a highlight of the number of tape-outs. We've got 3 tape-outs on FinFET technology alone, and we have 2 of which are with the CAM. And we have 19, actually that number has increased recently, so greater than 20 customers right now using our CAMs. And so this is a pretty well-proven technology. So another architecture that is helpful as far as increasing bandwidth and being able to manage data are asynchronous register files and multi-port register files. Some of these could be some very unique configurations, different configurations of read and write on the ports. So we've built several different types of these. We have a 4-port register file on the shelf at 28 nanometer that if you log into IP Marketplace, you would have access to that. And we also have pseudo dual port architectures as well. And those architectures are both targeting speed as well as we have a variant of it that implements the low leakage bit cell and is targeting the low leakage aspects of different markets. And then the bottom here just shows multi-ports. One customer came to us. They were at actually the 14, 16 nanometer node in the FinFET technology, and they were wanting to know what they could do with SRAM that would compete with density and efficiency of an embedded DRAM. And actually, we were able to come up with a novel approach with a pseudo dual port architecture that when you look at the efficiency of the performance over the area, it was an excellent approach. So there are various different types of these pseudo architectures that we can develop. But really at the bottom of it all is being able to use the 6T single port SRAM bit cell and then using logic and different techniques to get the most out of that to do multiple operations in a cycle. So where does this leave us? We've explored the fact that IoT is big business, very big business, and certainly an opportunity for all of us in the semiconductor area. And that really chip-level differentiation is at the heart of IoT competitiveness. This is with technology and IP selection of what's available and on the shelf today, as well as having the ability for optimized IP that can provide additional differentiation for your product. And then really being able to have IP that really targets that ultra-low voltage, low power aspect of those curves that we were talking about. And also, you need to have low-cost solutions. Many of these IoT devices are very low-cost devices, and they need to be very dense devices as well, where they have a very small form factor. And then, remember that there are the possibilities of alternative bit cell architectures that can be implemented. These types of architectures will enable you to run it at significantly lower voltages, typically trading off a little bit of area, but the advancement that you get on your battery life is incredibly significant. And then covering big data with CAMs, multi-port architectures, etc. So I invite you to join us on IP Marketplace at eSilicon.com Most of this IP, or many variants of this IP, are available today. The 40 nanometer and some of these ultra low voltage, there'll be instances made available in the next month or so. They're getting loaded as we speak, so that'll be happening over the next few weeks. But we have our IP available there from 180 nanometer technology all the way down to the 16 nanometer node. So I invite you to come join us, and I'll take your questions now.
Great.